Meet Bob. Bob is in his second year of mathematics at the University of Waterloo. He's taking his first course in statistics and is starting to recognize statistics problems in everyday life. Right now, Bob is learning counting techniques. So far, Bob has learned the addition rule, which states that if job 1 can be done in P ways and job 2 can be done in Q ways, then job 1 or job 2, but not both, can be done in P plus Q ways. The multiplication rule, which states that if job 1 can be done in P ways, for each of these we can do job 2 in Q ways. Then job 1 and job 2 can be done in P times Q ways. Finally, the probability of an event, A, is the number of outcomes in A divided by the total number of outcomes in S, where S is the sample space composed of all possible distinct outcomes of a random event, and A is a subset of S. Before class, Bob goes on his usual Tim Hortons run and buys a coffee. Roll Up the Rim is on. Tim Hortons advertises that the following prizes can be won: 40 cars, 100 prepaid MasterCards, 1,000 barbecues, 25,000 prepaid Tim cards, and millions of food drink prizes. Bob wants to calculate the probability of winning a grand prize. For purposes of this problem, Bob assumes that there are 5 million food drink prizes and that prizes are distributed evenly across all cup sizes and Tim Hortons locations. Given that Tim Hortons guarantees a 1 in 6 chance of winning any prize, Bob calculates that there are a total of 30,156,840 cups sold during the Roll Up the Rim campaign. To win a grand prize, Bob can either win a car, or a prepaid MasterCard, or a barbecue. By the addition rule, the probability of winning a grand prize equals the probability of winning a car plus the probability of winning a prepaid MasterCard plus the probability of winning a barbecue. This is equal to 40 cars plus 100 MasterCards plus 1,000 barbecues divided by 30,156,840 total cups. Thus, the probability of winning a grand prize is approximately 0.004%. Feeling lucky, Bob rolls up the rim on his coffee cup, but is invited to please play again. In fact, according to the National Weather Service's statistics on lightning safety, and assuming that Bob lives to the ripe old age of 80 years old, Bob is more likely to get struck by lightning in his lifetime than he is to win a Tim Hortons grand prize. After class, Bob and his roommate are playing Monopoly. It's Bob's turn. The next 3 spaces are go to jail and 2 properties occupied by hotels. Bob cannot afford rent. He quickly calculates the probability that he will roll greater than a 3 to bypass the next 3 spaces. The probability of rolling greater than a 3 equals 1 minus the probability of rolling less than or equal to a 3. Rolling a 3 can happen in exactly 3 ways: by rolling a 1 and a 1, a 1 and a 2, or a 2 and a 1. The total number of distinct rolls is 6 times 6, since for each of the 6 possible outcomes of the first die, there are 6 possible outcomes for the second die. Thus, the probability of rolling greater than a 3 is 1 minus 3 over 36, or 11 over 12. Bob feels confident that he will roll higher than a 3, so he goes ahead and rolls the dice. Bob rolls a 4 and lands on Community Chest. He picks up a card and is sent to jail. Poor Bob. The next day, Bob is walking down the street and is confronted by a magician. The magician bets Bob $10 that if Bob randomly selects 3 cards from a standard deck of 52 cards and puts them back in the deck, then he can make Bob's 3 cards appear at the top of the deck. Before betting, Bob calculates the probability of the trick. Using the multiplication rule and the fact that the cards are chosen without replacement, Bob determines that his 3 cards can be chosen in 3 times 2 times 1 ways, and the total number of possible outcomes that the magician can have is 52 times 51 times 50. Thus, the probability that the magician can randomly select Bob's 3 cards is 1 over 22,100. Realizing how small this probability is, Bob bets against the magician and goes through the trick. He picks 3 cards without replacement, memorizes them, and then puts them back into the deck at random. The magician shuffles the cards, says 3 magic words, and pulls Bob's 3 cards from the top of the deck. Unfortunately, Bob forgot that statistics don't apply in the world of magic. Bob hands over $10 and carries on his way. By the time Friday night rolls around, Bob is feeling down on his luck. He decides to hit the town and have a little fun. Bob finds himself in line at a nightclub. The bouncers are suspicious of fake IDs and are recording the birthdays of each person let into the club. There are 30 people in line, and Bob wants to calculate the probability that at least 2 people in line have the same birthday, an application of the birthday problem he read about in his course notes. He deduces that the probability of at least 2 people in line having duplicate birthdays is 1 minus the probability that everyone has distinct birthdays. First, Bob considers the number of outcomes in the sample space S. If there are 30 people in line, there are 365 possible birthdays for the first person, 365 for the next person, and so on. By the multiplication rule, the number of outcomes in the sample space is 365 to the power of 30. In order for each person in line to have distinct birthdays, the birthdays must be chosen without replacement, meaning that there are 365 possible birthdays for the first person, 364 for the second, and so on for each of the 30 people in line. This expression is simplified by the notation 365 taken to 30 factors. In general, n taken to r factors is equal to n factorial over n minus r factorial. Now, Bob simplifies the calculation and finds that the probability of at least 2 people having duplicate birthdays is 70.6%. While pondering this surprisingly high probability, Bob arrives at the front of the line. Unfortunately, Bob's birthday has already been recorded, and the bouncers suspect Bob's ID is fake. Although the statistics weren't in Bob's favor all week, all his practice calculating real-world probabilities helped Bob to earn an A+ on his stats return. Go Bob! The end.